Hello students, today we are going to solve some want-of factor numericals which appeared in 2024 CBSE question paper. First one is 1 molar aqueous solution of an electrolyte A2B3 is 60% ionized. So here 60% is degree of dissociation. Calculate boiling point of the solution. Before solving this question paper, I would suggest that if you do not know how to calculate I, which is want-of factor, please go through my previous video, link of which I'm going to give in the description box. To solve this, let's write the formula for elevation of boiling point, which is delta TB equals to IKBM. In case of degree of association and dissociation, we have to use these special formulas where we have to take care of want-of factor. Now this is because an electrolyte, the molecules will undergo dissociation, for which the equation is A2B3 is giving you 2A plus 3B, which means 1 mole of A2B3 dissociate to give 2 moles of A and 3 moles of B. At time 0, let us begin with 1 mole of A2B3 where A and B are 0. At time equals to T, let this alpha be the degree of dissociation. So if alpha is degree of dissociation, which means that out of one molecule or one mole, alpha moles are going to dissociate, which is going to be obviously a fraction if we are going to start with 1, or this degree of dissociation can be given as percentage even, but let's start with 1. Say if alpha moles undergo dissociation, then 2 alpha moles of A will appear and 3 alpha moles of B will appear. So now if we want to calculate I, we have to use the formula number of particles after dissociation divided by number of particles before dissociation. Now, after dissociation, number of particles, as you can see, are 1 minus alpha plus product particles, number of product particles, you can see 2 alpha plus 3 alpha, which is 5 alpha, divided by 1 particle before dissociation was 1. Now I am going to give a generalized formula for calculation of particles after dissociation. See, if 5 is the number of particles after dissociation, product particles, okay, and alpha is the number of particles undergoing dissociation, then if the general formula for this is going to be, see, let me write this first, 4 alpha, right, by 1. Now in this case you can see that generalized formula can be written as 1 plus n minus 1 alpha, where n is the number of product particles, right, because number of product particles were 5 and in the formula you are getting 4. So number of product particles minus 1 in bracket and multiplied by alpha. Okay. So here if we calculate I, we are going to do 1 plus 4 into alpha is 60%, right? Degree of dissociation is 60%. So let's calculate. It's going to be 1 plus 12 by 5, which comes equal to 1 plus 2.4, that is 3.4. So I want a factor for this particular equation is 3.4. So let's keep this in this formula. Delta TB, as I have discussed in previous video, is equal to T solution minus T solvent. So let's keep this in the formula. T solution minus T solvent equals to I, which we calculated 3.4, Kb, which is given 0.52, multiplied by molality, which is given 1 mole. So we have to calculate boiling point of the solution, and since it is water, boiling point of solvent would be 100 degree Celsius, or we do not use degree Celsius values, we use Kelvin values, which is 373. So T solution minus 373 equals to this, if we calculate 3.4 into 0.52, comes out to be 1.768. Therefore, T solution will be equal to 1.768 plus 373, which is 374.768 Kelvin. So this is the answer. Next numerical is a glucose solution, molar mass 180 gram per mole, is isotonic with 2.5% solution of an unknown organic substance. Calculate molar mass of the organic substance. So isotonic means osmotic pressure of glucose is equal to osmotic pressure of the organic substance. So let pi 1 be the osmotic pressure of glucose solution and pi 2 be the osmotic pressure of unknown organic substance. We have to do pi 1 equals to pi 2. Now formula for pi we saw in the colligative properties video, which is equal to mass of the substance divided by molar mass of the substance multiplied by gas constant multiplied by absolute temperature divided by volume of the solution. So changing this formula for pi 1 and pi 2, we can write W1 by M1 into RT by V equals to W2 by M2 into RT by V. RT by V is same for both the solution. W1, which is mass of the glucose or amount of the glucose taken, is 6 gram, and molar mass of glucose is 180 gram per mole. Let us cut these which are same and on both the sides, and W2 is equal to 2.5 gram. 2.5% solution means 2.5 gram substance is dissolved in 100 ml solution divided by molar mass we have to calculate. So let's keep M2. Therefore M2 will become 2.5 into 180 divided by 675 gram per mole. The next numerical is the vapor pressure of a solvent at 283 Kelvin is 100 millimeter Hg. Calculate the vapor pressure of a dilute solution containing 1 mole of strong electrolyte. Strong electrolyte means it will dissociate completely. Okay, in 50 moles of solvent at 283 Kelvin. Yeah, so they have also provided that assuming complete dissociation, because it is a strong electrolyte, even if they are not giving, you are going to assume it as the electrolyte is undergoing complete dissociation. That means degree of dissociation is 100%. Electrolyte is A, B undergoing dissociation to give you A plus B. And in the beginning you are taking 1 mole, 0, 0 at time t. Since degree of dissociation is 100%, that means all of the moles are undergoing dissociation. So 1 mole of A will appear, 1 mole of B will appear. And as I given you the formula for I in the previous slide, 1 plus n minus 1 alpha divided by 1. So 1 plus n here is 2 product particles, number of product particles is 2. So 2 minus 1, alpha is 100%. So let it keep as 1. Vapor pressure, lowering of vapor pressure, relative lowering of vapor pressure is delta P, or it is P0, that is pressure of pure solvent, minus PS by P0 equals to I, since it is a dilute solution, N by N. So this is going to come out as vapor pressure of solvent P0 is given as 100 millimeter Hg, and calculate the vapor pressure, that means PS you have to calculate, it's not given. What else is given? They have given 1 mole of strong electrolyte. So N equals to 1 and capital N equals to 50. So let's keep the values over here. P0 is 100, PS you have to calculate, divided by 100, equals to I we calculated to be 2, N is 1 and capital N is 50. So this is equal to 100 minus PS equals to this 100 you take up here on the other side by 50, which is going to give you 4 minus 100. So PS equals to 96 millimeter mercury. Next numerical is, a solution is prepared by dissolving 5 gram of non-volatile solute in 200 gram of water. It has a vapor pressure of 31.84 millimeter mercury at 300 Kelvin. Calculate molar mass of solute. Vapor pressure of pure water at 300 Kelvin is equal to 32 millimeter mercury. Okay. The formula for lowering of vapor pressure again is P0 minus PS by P0, pressure of pure solvent minus pressure of solution divided by pressure of pure solvent is equal to W1 by M1. W1 is mass of the solute, M1 is molar mass of the solute multiplied by M2 by W2, where M2 is molar mass of the solvent and the W2 is mass of the solvent. So let us write the values here. W1 equals to, they have given 5 gram M1 we have to calculate, M2 because this is solvent is water, right? So M2 is equal to 18, and W2 they have given 200 gram of water, so 200, and vapor pressure of pure water P0 they have given, which is 32 millimeter Hg, and vapor pressure of solution, which is PS, they have given 31.84 millimeter Hg. So keeping all the values in the formula, we have 32 minus 31.84 divided by 32 equals to 5 by M1 we have to calculate, multiplied by 18 by 200. Solving this, we can get 5 into 18 by 200 into 32, and this 32 minus 31.84 is 0.16. So 0.16 we are going to keep here. (90 gram per mole is the molar mass of the solute. And the last numerical is 18 gram of non-volatile solute is dissolved in 200 gram of water, freezes at 272.07 Kelvin. That means this is depression of freezing point. That formula you have to apply. Calculate molar mass of the solute. This is an easy one, direct formula application is there. So the formula for molar mass, which is M1, say molar mass of solute is M1, is going to be Kf into amount of the solute multiplied by 1000 divided by amount of the solvent, which is water here, and multiplied by depression in freezing point. Depression in freezing point is equal to 273 minus 272.07, which is 0.93 Kelvin. Kf is given 1.86. W1 is given 18 gram of non-volatile solute, they have said, multiplied by 1000 divided by W2, 200 gram of water is there, and delta Tf is 0.93 Kelvin. So this comes out to be 180 gram per mole.